In today's lecture, we're going to consider some practical calculations of a multi-component universe. So I'm going to call this Fun with Time and Space in a multi-component universe. For a quick summary, let's recall that the Friedmann equation can be written as the Hubble parameters divided by h naught. And let's actually put the square outside, is equal to omega lambda 0 plus omega k0 times a0 over a squared plus omega matter 0 times a0 over a cubed plus omega radiation 0 times a0 over a to the fourth. And as the universe expands, each of these terms will dominate the expansion of the universe. So, for example, this term dominates at late times, while this term dominates at early times. And so there is an epoch of dominance for each of these terms. Next, we're going to talk about practical calculations. All right, so the Friedmann equation, which is just this equation up here, that h squared is in essence an equation for dA by dt is equal to a times h naught, and then the square root of all that stuff that's on the right-hand side. And we'll just put that in brackets. So in general, that's the equation, that's the ordinary differential equation that one will be solving to find the evolution. Now, when we calculate times and distances, it's convenient to rewrite this in a dimensionless form. So for example, x is equal to a divided by a0. If we make this substitution of variable, then dx is equal to dA divided by a0 In addition, this x, which equals a over a0, is also equal to 1 over 1 plus z. And this leads to dx equals minus dz divided by 1 plus z squared. So we can rewrite this differential in terms of x or in terms of z. And in fact, what we're going to do next is we will find later that we are going to want to integrate over dx or over dt. So what I'm going to do right now is I'm going to go ahead and use this. We're going to use this variable, the substitution of x equals a over a naught, and substitute it in this expression to give us an expression for dt. So here we could just put dt on the right-hand side, and then the stuff that's on the right-hand side divided out so that's on the left-hand side, and we have dA over this quantity. But instead, I'm going to use x. So we have dt is equal to dx over h naught times x, and then the square root of everything that's in the bracket. And so now this infinitesimal displacement in time, dt, is written in terms of a dimensionless displacement in this variable x, and then the 1 over h naught gives it the units. Or if we're going to do this in terms of z, then we can say that dt is equal to minus dz over h naught, and then 1 plus z is in the bottom, square root, and all the stuff that's in the bracket. So once again, what's in the bracket is, if we go up here, it's all the stuff that's on the right-hand side up here. So for example, if we want to find the age of the universe, age of the universe, given this multi-component universe, then we just integrate the left-hand and the right-hand sides. So we're going to integrate from 0 time to some time later, dt, which is equal to t. And this equals the integral of the right-hand side. So 0, x, and integrating dx, h naught x, square root, everything in the bracket. And sometimes this integral on the right-hand side is analytic, and sometimes you're going to need to solve it numerically. But in general, this is the age of the universe for any multi-component. And last time we calculated the age of the Einstein de Sitter universe. So let's go ahead and use this formalism just to be complete. Since you already saw it, let's do it again using this formalism. So Einstein de Sitter age. So we have that omega m0 is equal to 1. Omega k0 is equal to 0. And which also the radiation component and the cosmological component are also all 0. All right, so now we have t is equal to the integral from 0 to x dx, and then h naught x on the bottom, and then we have the square root, the stuff in the bracket. Now, omega 1 is 1, and all the others are 0, and so the only term that's left is x to the minus 3. All right, so this equals 1 over h naught. 1 over h naught, remember, is the Hubble time. It's a characteristic time of the universe, integrating from 0 to x. And then this is x to the 1/2 dx. And we find a solution of t is equal to 2/3 x to the 3/2 1 over h naught. And remember, x is equal to a over a naught. So any time in the past, a is smaller than today, a naught. So x will be less than 1. And if you want to evaluate this for the age of the universe today, you just say that x is equal to 1. Otherwise, you would put some other value of x there, and that gives you the age of the universe at that scale. And so for x equals 1, which is today, we have that t is equal to 2/3 times 1 over h naught. And that's what we got last time. All right, so we can do this for some other interesting analytic cases. So let's consider a flat, radiation-dominated universe. So this is one in which the energy density of the universe is dominated by photons just flying around. All right, so it's flat. So that means omega k0 is equal to 0. We're dominated by the radiation, so everything else is 0 except for the radiation. So let me go ahead and just explicitly write that down. All right, these are 0. And then omega r0 is equal to 1. This time t is equal to 1 over h naught, integrating from 0 to x of x dx, which is equal to 1 over h naught 1/2 x squared. All right, so that would be the age of the universe, and we plug in x equals 1 for today. A over a naught is equal to 1. That would give us the age of the universe. Or, well, let me just write that down. So for x equals 1, this gives us that the age is equal to 1/2, 1 over h naught. Now, if we go back to this expression, t is equal to 1 over h naught 1/2 x squared. Well, x is a over a naught, and so this gives us our solution for a over a naught. 2 times h naught times t to the 1/2. And if I draw this evolution, t, we'll do x equals a over a naught. Then we have that, oops, where this is, this curve is proportional to t to the 1/2. Let me rewrite that. 1/2. And once again, we have a of 0 is equal to 0, and a dot of 0 is infinite, and we have a Big Bang. All right, so we're going to do, next, we're going to do flat. and dominated by cosmological constant. All right, and so in this case, all the others will be 0 except omega lambda 0 is equal to 1. Okay. So in this case, we're going to integrate dt, and I already know that the solution is going to be a natural log on the right-hand side, which suggests to me I need to be careful about the limits of integration over here. So I'm going to say we're going to start at some reference time t0 and go to some other time t. And then this is going to equal, the right-hand side is 1 over h naught. And this time we're going to integrate from, let's say t0 is today. So we'll say x is equal to 1 today, and then to some future value of x. And the integral this time is dx over x. And the solution to this is h naught times t minus t0 is equal to the natural log of x. And so now the solution is that x equals a divided by a0 equals e to the h naught t minus t0. So for the case of a cosmological constant, the evolution of a over a0 over x is an exponential. Oops, that needs to be a minus sign. And there is no Big Bang for that solution. Okay, so in summary, what we just did is we calculated the age of the universe for any of these types of universes by just evaluating t is equal to the integral from 0 to x of dx over h naught x square root of the stuff in brackets. All right, so that's fun with time and understanding the connection between time and the age of the universe. Now, in here I write down x. I could also express this in terms of z as well. So if you want to know the age of the universe that corresponds to some particular redshift z, then you can use this to calculate that. All right, so next we're going to use what we've just learned, this trick of transforming this dt into dx and then doing the integral. We're going to use that in the context of the luminosity and angular diameter distances as well. So now we're going to calculate luminosity, luminosity and angular diameter distances. in a multi-component universe. I'll just remind you that the typical time scale is over order 1 over h naught. And so when we were calculating the age, we ended up with a dimensionless integral, and then we would just multiply it by 1 over h naught, and that gives you the age of the universe. But the details of the multi-component universe go into calculating that dimensionless integral, that dimensionless constant that comes from the integral. Similarly, when we do these distances, we're going to find that there is going to be a integral, and it's going to be dimensionless. And in front of that dimensionless integral, there will be a distance scale that will be of order c over h naught, or the Hubble distance. All right, so the question is, how does one calculate the angular diameter distance and the luminosity distance? We're going to go over some of the important details here. So the angular diameter distance, if you recall, is a0 times L, this function L of r, which represents a co-moving function, divided by 1 plus z. And ultimately, the question is going to be, what is r? And that's what we're going to calculate. All right. And the luminosity distance is equal to a0 times L, which is a function of r, times 1 plus z. And we have that this L of r is either sine of r, if k is equal to +1, or it's r, if k is equal to 0, and it's hyperbolic sine of r if k is equal to -1. Okay, and so the question is going to be, what is r? And so that's what we're going to evaluate next. We're going to start with the interval, the light-like interval. So the interval is equal to, for the Robertson-Walker metric, minus c squared dt squared plus a squared times dr squared plus L squared, and then times d theta squared plus sine squared theta d phi squared is equal to 0. So we're using this light-like interval to give us a connection between dt and dr. And we're going to consider some path between us and some distant place on the radial coordinate. So this is going to be equal to 0. That's going to be equal to 0. And so now we have that c dt is equal to minus a dr. And this leads to the integral of going from some time in the past to today, c dt over a is equal to minus, we're integrating from r, so photon started at some r distance away and is coming to us, so from r to 0, dr is equal to r. So if we want to know what is the luminosity distance or the angular diameter distance, we first need to know what is r for that particular position in that distance. What is r given the cosmology? So this is what we're going to do. We are going to use the Friedmann equation to replace dt in the integral for r. You see up here that in order to figure out what is r, what is that co-moving distance to that point, we need to integrate c over a over dt. All right, so recall that dt is equal to dx over h naught x square root, all that stuff in the bracket. Now, if we take this and plug it into the integral for r, which remember is c times the integral from t to t naught dt over a. This is equal to c over h naught. There is that characteristic Hubble distance. And we're integrating from some distant place, r, or x in this case, to today, or 1. And then we have dx over a times x square root, that stuff in the bracket. And I'll remind you that x is equal to a over a0. So we can plug this in. To that up there, and we get that r is equal to c over a naught h naught, integrating from x to 1 dx x squared square root bracket, and that is how we find the co-moving distance. And you notice that c over h naught is a characteristic Hubble distance, and we're dividing by a naught, the scale of the universe. And so this this co-moving distance will remind you this is a dimensionless co-moving distance. So it's c over h naught divided by a naught. All right. And now that you have r, and sometimes this r can be analytic, but often, especially if you're considering the general multi-component case, it's not analytic, and you have to evaluate this integral numerically. Once you do that, to find the angular diameter distance, it would be a naught times L of r divided by 1 plus z. Or to find the luminosity distance, it's a naught times L of r times 1 plus z. All right, there's a few other tricks when calculating this L of r, or there's one other main trick. I'll highlight it here. So let's write down this function L of r again. All right, so it's sine of r for k is equal to +1. It's r for k is equal to 0. And it is hyperbolic sine of r for k is equal to -1. Let's go ahead and put a little squiggly bracket here. All right, so the case in which L of r is equal to r, the one in the middle in which k is equal to 0, let me go ahead and do that one first. So in that case, we have a of 0, right? So in either the angular diameter distance or the luminosity distance, we have a of 0 times L. So in that case, a of 0 times L of r is equal to a of 0 times r. And you notice that r has c over a0 times h0, and the 1 over a0 in r will cancel with this a0, and we will be left with an angular diameter distance that's proportional to c over h naught. And it's the same with the luminosity distance. In either case, that will be proportional to c over h naught. For these other two cases, there's a little trick that I'm going to show you that you're going to need to do. So you're going to need to figure out what is omega k0 on the inside or of the integral. Or maybe you're given omega k0 and you might want to calculate what is a naught and h naught. And because you're not going to be able to, when you have sine of r and hyperbolic sine of r, the a0 that's in front here is not going to cancel with that. So what do we do about that? Well, we're going to notice that omega k0 by definition is equal to minus c squared k over a naught squared h naught squared. And we immediately see that there's a correspondence between omega k0, a0, and h0. K is a constant that will be 1, 0, or -1. C is the speed of light. And so this expression, as long as you know h naught, you don't need to know both omega k0, a0. This gives you an expression between omega k0 and a naught, as long as you have h naught. So in either of these cases where k is -1 or +1, then we find that c over a naught h naught is equal to the square root of the absolute value of omega k0. And so since c over a naught h naught is equal to that square root absolute value of omega k0, if you know omega k0, you can plug that into this expression here for whatever it is, and now you would have your value for r. You also can rewrite this. So let's see, for example, a0 is equal to c over h naught divided by square root of the absolute value of omega k0. I think I did that right. Yeah, I think I did that right. All right, and that's how you calculate the co-moving distance r, so that you can then calculate the angular diameter distance and the luminosity distance. Before we complete this lecture, there's one other concept that I want to touch upon. It's kind of fun to consider. Let's ask this question. What does it take to stop the expansion of the universe? In particular, when omega lambda does not equal 0, when there's some cosmological constant. So let me sketch possible trajectories. Before I introduce the cosmological constant, I showed you possible trajectories for A, in which all we had was cold matter. Well, there was the critical curve in which omega matter equals 1. So we'll call, right? And then omega k was equal to 0. There is this curve in which omega matter is greater than 1. And then there's this curve in which omega matter is less than 1. This is when omega lambda is equal to 0. And so what it takes to stop the expansion of the universe and to make it contract again was this condition here. The omega matter is greater than 1. When you add a non-zero cosmological constant, that is no longer the case. Right? So what about when this does not equal 0? Well, we're going to notice that what we're looking for is we're looking for when A dot is equal to 0. When do we have possible solutions so that A dot is equal to 0? When is it that the curve goes up, it stops its expansion, and then goes down? So when does A dot equal 0? Well, we can use Friedmann's equation to help us with that. So A dot over A squared is equal to H naught squared times all that stuff in the brackets, all that omega stuff, and the omega k, or the curvature term. And we want to know, when is A dot equal to 0? Well, that's equivalent to asking, when is this equal to 0? It's not exactly the same thing, but it's equivalent to, right? Because we're dealing with A dot squared. If H0 is some value today that is non-zero, then this is equivalent to asking the question, where do we have solutions where the stuff in brackets equals 0? Let me explicitly write that down. Omega lambda equals omega lambda 0 plus omega k 0 x to the minus 2 plus omega m 0 x to the minus 3 plus omega radiation 0 x to the minus 4. We're going to ask, when is this equal to 0? And you would find the solution such that define the solution for x such that this is equal to 0, given the non-zero value for each of these values. That will give you, if there is a solution, then that will give you when the universe stops its expansion and reverses and comes back down. And if you do this exercise, you will find there are values for omega lambda 0 in which you can get the universe to collapse. So even though dark energy is thought to cause acceleration and expansion of the universe, there are values for omega lambda 0 such that you will still get a collapse. All right, it's just the details. And just as if you want to do this on your own, just as a practical aside, it's easier to set this up as a cubic equation. So multiply both sides by x cubed, and you will get omega lambda 0 times x cubed plus omega k 0 times x plus omega matter 0 plus omega radiation 0 x to the minus 1 equals 0. All right, so why did I do that? Why did I not just do x to the fourth? Well, it's a little easier this way. In particular, in most cases that you're going to consider, this is still roughly of order 0. This is approximately 0. And so it truly does become a cubic function that you're trying to find a solution for.